need these partial derivatives for the last section of the class, 6.3. And that is the end of the material. Okay, so what are they asking us to find here is fx, fy, fxx, fxy, fyy, fyx. Therefore, but I can get there before I find these. Oh, sorry. I forgot to stop sharing. Sorry. So, they're asking us to find the four second order derivatives, partial derivatives. And you will see that fyx and fxy must be the same. Then why bother? We have to make sure that they get to be the same. Okay, so we have to determine four, but these two will be the same. So we have to find the first order, fx and fy, because otherwise I cannot find fxx, fy, fxy, fyy, and fyx. Okay, so let's start slowly but surely. Okay, 7. Okay, so let's find fx. So let's look at this function and ignore y, because y is a constant. And let's differentiate. You cannot ignore by not writing it, but you will ignore it when you differentiate. So can anyone differentiate this with respect to x? Not as a product rule, because y is a constant. Assume that y is 15. So you're not going to differentiate, you're not going to use the product rule. So, can anyone tell us what to write? 3x squared y, differentiated only with respect to x. Yes, please, anyone, please. It's okay if you're wrong.
6x.
We cannot ignore y. Yes, that's it. So this part is done. We differentiated this with respect to x. Now I am here. We only differentiate with respect to x, but we cannot delete y.
Would it be minus 2y?
That's it. Is there x in here?
No.
No.
So 4y?
4y prime is 0. Y is a constant.
Right.
Excellent. So this is done. I want to move on to fxx. We want to differentiate this function with respect to x only. So let's look at the first term.
Would it be 6x what? Oh. 6y.
That's it. Is there x in here?
No, ma'am.
So there's a constant. Constant prime is done. Okay, so we're done with this, done with this. Let's find fy. Back to the original. Can anyone differentiate this with respect to y?
Would it be 3x squared?
That's it. Let's differentiate this with respect to y.
Minus 2x?
That's it. Let's differentiate this with respect to y.
Plus 4?
That's it. Awesome. So this is done. I want to jump to fyy. I want to differentiate this function with respect to y. Is there any y?
No.
So the answer is
3x squared minus 2x plus 4?
constant, constant, constant.
So 0?
That's it. So this is done. Now I want to determine fxy. I go back to fx, and now I differentiate this with respect to y. It's already differentiated with respect to x. Now we differentiate with respect to y. This with respect to y.
Would it just be 6?
But what happened to x?
is a 6x.
Good. We differentiate this with respect to y.
Just minus 2.
That's it. Awesome. So this is done. Now we want fyx. I go to fy. And right here, I differentiate this with respect to x.
Six x minus 2.
They have to be the same. If they're not the same, I'll say oops and go back to the drawing board. They have to be the same. Okay. Much better. Okay, let's look at one more. Feel free to choose. Your turn to choose whatever you want. And then we'll finish up with 6.3. You'll see where this is used and why we need it. Okay, I will choose 29. So, f of x comma y equals x to the fourth, y to the third, minus x squared, y to the third. Sounds difficult. Not at all. Fx and then fy. We differentiate this with respect to x. Please try. It's okay if you're wrong. Yes?
4x to the third, y to the third.
Excellent. That's it. Perfect. We're differentiating this with respect to x.
Would it be minus 2x, y to the third?
That's it. Perfect. Fy. We're differentiating this with respect to y.
X to the fourth, and then 3y squared.
That's it. Excellent. Minus. We differentiate this with respect to y.
Um, 2x, 3y squared.
With respect to y.
Is it 3x squared y to the third?
You mean second, because we subtract. We brought the 3 down and we have to subtract 1 from the power. Agreed?
I guess I'm confused at why we're putting it in front of the x though.
So when I write 2 times 3 times 4, I can write it as 4 times 3 times 2, and I can write it as 3 times 4 times 2. So when I have here x squared times 3y squared, I'm not going to write it like this. It has to be written as 3x squared y squared. I'm not going to leave a constant in the middle of a product. So because multiplication is associative, in other words, 2 times 3 times 4 is 4 times 2 times 3 is 3 times 4 times 2, and I can combine them in any way, shape, or form. So the constant has to stay in front. Very good question. Is it clear?
It's better.
Perfect. Good. So we determine fx and fy. Now let's determine fxx. We're differentiating this with respect to x.
Would it be 12x squared? 27y to the third.
Good. Awesome. Here, with respect to x.
Minus 2y to the third.
That's it. Awesome. fyy. We differentiate this with respect to y.
2y and then 3x to the fourth.
You mean 6, x to the fourth, y. Perfect. Minus.
6x squared y.
That's it. 2 more. Back to fx, because we want fx, and now with respect to y. We differentiate this with respect to y.
Would it be 12x to the third?
Yes.
Y to the second?
Yes. Minus. With respect to y.
Minus 6x y to the second.
That's it. We have one more. Last one. Fyx. We go back to Fy. Here's Fy. And now we differentiate this one with respect to x.
12x to the third, y to the second?
Yes, 12x to the third, y squared. We differentiate this with respect to x.
6x y squared.
Yes. They have to be the same. And they are. Which gives us tremendous confidence that we are on the right track. Okay, I want to share my screen for a second and show you something on page 570. We know how to graph functions with one variable, but graphing a function that has two variables in it is giving us something like this. This is a three-dimensional space where x variable is measured on this axis, y variable is measured on this axis, and the function itself, f of x, is measured up here. When the computer software creates this a function of two variables, x, y, and this is the variable, right? This is the dependent variable. Sometimes it has, or they show that it has a maximum. This is a relative max. This one, for example, computer generated, it has a relative min. It may have two. It may have a relative max, another relative max, and it may also have an absolute or a relative minimum, right? This is the absolute also. We discussed that when we looked at functions of one variable with on a closed interval, absolute max, absolute min, relative max, relative min. So this is the purpose of looking at partial derivatives. Why? Because when we determined the max or the min, that's what we did for functions of one variable. We determined the critical numbers. We found the derivative. We found the critical numbers, and then so on and so forth. The same thing here. We are given a function of two variables. We're not going to go beyond just two variables, maximum. And we're asked to find the relative max and the relative min. And there is a procedure for doing that. So I'm going to jump directly to page, that's the last topic of this class. And this is page 576. So they're giving us find the relative max or min value of the function. So we have plenty of examples here. We are not going to deal with problems 15 through 18 because we will not discuss the constraint. This is a constraint. Okay? Find the max min knowing that this is a constraint. Find the max min knowing that this, no, we're not going to deal with this. So we're going to look at problems 1 through 14 and of course word problems. And that's the end of the course. So please choose a problem from 1 through 14, if not I will. So I can show the procedure of finding a max min for a function of two variables. It's a step-by-step procedure. And you will see how interesting this is. I hope you find it interesting. If you don't choose, I will. I will choose, I don't know, 7. You can choose the next one. So hopefully I have time to finish. I want to finish at least one problem. So x squared plus 2xy plus 2y squared minus 6y plus 2. So here are the steps. Like before, with the function of one variable, we found the derivatives, or the derivative, we set it equal to 0. But this time we have to find two derivatives. So this is our first step. We find the first order partial derivatives. Again, first order partial derivatives. Okay, that's our first step. So coming back, can anyone help with fx and fy? We are differentiating each term with respect to x. If it doesn't have x, the derivative is 0.
So 2x
Excellent,
plus 2y
excellent.
plus 2y squared.
With respect to x, if it doesn't have x, it cannot be anything.
Okay, so it's just nothing.
Nothing. That's it. We are done with fx. Awesome. Now we go back and we differentiate each and every term with respect to y. If it does not have y, it's nothing.
So the first one is nothing.
Good. With respect to y,
Plus 2.
with respect to y,
Do what?
with respect to y,
2x.
that's it. With respect to y,
4y
yes. With respect to y,
minus 6.
with respect to y, who cares? It's a constant. That's it. That's our first step. In step number 2, like we did with the previous, in the previous situation with one variable, we set these two equal to 0 now. This is our second step. Initially we had one variable, so we set f prime equal to 0. Now we have to set them both equal to 0. 2x plus 2y equals 0. 2x plus 4y minus 6 equals 0. We have to solve the system. Because now, as you've noticed on the graph that I showed you, we have to find, if any, we have to find an ordered pair. Okay, so notice that here I can divide by 2 and move y to the other side. So x equals negative y. I got this from here. I divided both sides by 2 and then I moved y to the other side. I will use substitution and replace x by negative y. So negative 2y plus 4y equals 6. 2y equals 6 means y equals 3. I have the y variable, or y coordinate. Now I need to determine the x coordinate. What will the x coordinate be? X equals the opposite of y. Y is 3. What will be the x coordinate?
-3.
Negative 3. So I